Sequences. We've talked about sequences already, the main part of them. An ordered set of numbers is what a sequence is. Each term in the sequence is separated by a comma. And a sequence may be infinite, which means it goes on forever, or it may be finite, which means it has a limited number of terms. We can think of a sequence as a function with sequential natural numbers as the domain and the terms of the sequence as the range. Right? So we have the term numbers and then the term values. Now notice that they use a sub n here to represent the term values. So we're going to use subscripts still, okay, to represent the term number. Now there's two different ways that we can look at terms. One is using recursive formulas to be able to find the next term in a sequence, and another way is using what's called an explicit formula. A recursive formula just tells us to use the previous term to get the next one, okay? Which is what a lot of you do, what you do most of the time anyways. Take my last term, do something to it to get the next term. All right? And so recursive formulas actually are always using subscripts, and they say, okay, here's a formula, and I'm going to find the next term using this formula. And so with a recursive formula, we see it written something like this one here, which says a sub n equals 3 times a sub n minus 1 plus 2. Well, the a sub n minus 1 is the previous term, and a sub n is the new term I'm trying to get. So whenever you see a sub n minus 1 or a sub n minus 2, right, that means we're using previous terms to get the next term. And that's called a recursive formula for that reason. So all this says then is we're going to start with a sub 1 equals negative 2. So our first term is negative 2. And to get the next term, we're going to multiply it by 3 and add 2 to it. So we'll do 3 times negative 2 plus 2 to get the next term. So negative 6 plus 2, negative 4. Then we'll use that answer to get the next one, because we're going to use our last answer then to get the next answer. So 3 times negative 4 plus 2. Negative 12 plus 2 is negative 10. And then we use that answer to get the next one. So negative 30 plus 2 is negative 28. And then we use that one to get the next one. That would be negative 82. So using the recursive formulas, whenever you see a sub n minus 1 in a formula, then that tells us that we are going to be using the last answer to get the next answer. And this is actually the process of using your calculator to do this also. That you're using we can use the last answer feature on our calculator. So if you take your calculator, show you how to do that. So with our calculator, we can put in negative 2. All right, so we're storing that answer then for our last answer. And then if you look where your negative key is, it's got answer there, ANS. So if I do 3 times the answer, right, that's the last number I just got, plus 2. And this is a method of doing using a recursive formula with our calculator. And we can do it on the calculator. So we store the first term. The answer key represents a sub n minus 1. And then after that, all we actually have to do is press enter, and it will give us our next number. So that's the recursive formula for finding the next terms of the sequence. So one of the things to remember is that if it says find the first 5 terms of the sequence, they've already given me the first one. So I only need to find 4 more. Okay. So this is recursive formulas when we have a sub n minus 1. Right. Now the other type of formulas are what's called explicit formulas. And explicit formulas are basically like a y equals. The only difference is we're using a sub n still for our answer, but in the formula we're just putting n in there, and n refers to the term number. Okay? So n is always going to be the term number. So in this situation, all we're going to do is plug in the numbers 1, 2, 3, 4, and 5, put in the term numbers for the value of n to find the next term. So when we use an explicit formula, all we're doing is plugging n in, or plugging the term number in for n. And this is one you actually could do right in your y equals of your calculator, because all we're doing is plugging specific numbers in from a table. So we have 3 to the first power minus 1 is 2. Now, this number is not what I'm using, all right, because I'm not doing recursion, so we're not using the last answer, we're using the term number. So 3 squared minus 1 is 8. Then 3 to the third power minus 1. And 3 to the fourth power minus 1. And 3 to the fifth power minus 1. So we're using the term number replaces n in the formula. To get the term value. So the term number replaces n in the formula to get the term value then. So here we got 26, 80, and is that right? 242? Okay. 81 times 3 minus 1. Okay. So the explicit rule is different in the fact that we're just replacing the term number for n. In a recursive, we replace the answer for a sub n minus 1. Okay, so just have to make sure you pay attention to the difference between recursive and explicit formulas. Recursive, we use the last answer feature of our calculator we can to find it. And with explicit, we can actually put it in our y equals and find it. All right, so now we can use our knowledge of functions to write rules for sequences. Reminder that linear patterns have constant first differences, quadratics have constant second differences, and exponential patterns have constant ratios. So when we say we're writing an explicit rule, we're finding the function. And when we write the function in this case, we're going to say a sub n equals, and n is going to be our variable. So instead of saying y equals something with x be the variable, or f of x equals something with x be the variable, when we're talking about sequences, we're using a sub n as our y equals, basically, our function, and n is the variable that we're going to use. Now, most sequences, you can tell what type it is right away. We've practiced it already, finding arithmetic and geometric ones, so we know when we're multiplying or when we're adding or subtracting. Okay. Those are usually pretty easy. The ones that are a little bit tougher are the quadratic ones sometimes. But we have a method we're going to use to do this. So we're actually going to make a table to do it. Now, if you are unable to figure out what it is, we actually could use regression from our calculator to do it. And what I'm going to do is I'm going to make a table using term numbers and the term values to be able to figure out what our formula is. So I'm going to put, what do we got, 5 of them. Oops. So in this table, I'm going to put the numbers 1 through 5 that represent how many terms I have in my sequence. And so instead of actually using ratios, first differences, or second differences, I'm actually going to use this table to do it instead. And then I'm going to put the term values in here. And then from there, I want to figure out what happens from the first term to get to the terms after that. Okay? So I'm going to start with the first term and figure out, okay, so what am I doing from there to get all the rest of the term values then that we're working with? Okay? So, to get from 5 to 10, we are multiplying by 2. All right? So this is 5 times 2 to get the second term in this sequence. All right? So what do I do to get to the next term in the sequence? Okay, we're multiplying this one by 2 again, right? Okay, so if I multiplied by 2 once to get 10, I'm going to multiply by 2 twice to get 20, right? Because I'm multiplying by 2 again. So then to get 40, what would I do? All right, so I'm going to multiply by 2 another time, which means I'm going to multiply by 2 to the third power. And then multiply by 2 to the fourth power. All right. So, to get the nth term, we can see a pattern, right? Each one of these has a 5. They all have multiplying by 2 but raised to a power. Now the key to this is, how does the power then compare to the term number that we're on? So when I'm on term 2, my power is 1. So it's 1 less. So this is going to be then 5 times 2 to what power? Okay. No, not the fifth, because I'm doing the nth term, so it would be n minus 1. So my rule for this is a sub n equals 5 times 2 to the n minus 1 power. So I just wrote the explicit rule for it. Okay. Now the difference is that with your calculator, if your calculator was doing it, it all goes back to basically term 0. It would write a rule for you as if there was a term 0. Since we don't have a term 0, then we write them like this. Okay. So you're probably going to have that n minus 1 in each formula that you write, whether it's linear or exponential. So if you remember when we did we could go back even further here and do it, but we'll leave it right there. All right. So here's another one. All right, so in this case, what are they doing to get from the first term to the second term? Or to the third term or the fourth term? What are they doing each time now? Well, let's see. If we try first differences. So 4 minus 1.5 is 2.5, right? 6.5 minus 4 is 2.5. So each time we are adding 2.5, right? Okay. So to get to the second term, we're doing 1.5 plus 2.5 one time. And then to get to the third term, what are we doing? We're adding 2.5 again, right? Okay. So that means we're doing 1.5 plus 2.5 times 2. Because we're using it twice, adding it twice. Get to the fourth term, we're going to add it 3 times. And so on. So to get the nth term, we would have 1.5 plus 2.5 times n minus 1. So a sub n equals 1.5 plus 2.5 times n minus 1. Now that's one answer you might get. Now usually when they're going to give you linear models, they're going to want you to, or if it's an arithmetic sequence, they're going to want you to simplify it a little bit more. So when they simplify a little bit more, we want this, instead of it being n minus 1, we would like it to just say n. Okay? So we want to simplify this expression. Well, there's an easier way to do it. I mean, one way is we could just distribute the 2.5 and simplify it. Or we could work backwards. So if we actually put in here, all right, let's say there's a term 0. Well, if I'm adding 2.5 each time to go down, to go up, we would have to do what? Subtract 2.5. So what's 1 point? So this would actually be 1.5 plus 2.5 times negative 1. Right? Because this one here would be 1.5 plus 2.5 times 0. All right, well, basically all we're doing then is subtracting 2.5. So what's 1.5 minus 2.5? Negative 1. So another way I could write it is a sub n equals 1.5. Oops, excuse me, not 1.5. Negative 1 plus 2.5 times n. So either of these two answers would be okay. Right? But when it is linear, then you should go to this point. Right? So whether that means you take this expression and you just simplify it, or whether it means you work from term 1 to term 0 and find it. Okay? But making a table doesn't always work, but it helps you to see this table I made here helps me to see what's happening from one term to the next. So I can say, okay, so how does my n come into play with this? And that isn't always the case, but most of the time it is. Okay. Physics application. Ball is dropped and bounces to a height of 4 feet. The ball rebounds to 70% of its previous height after each bounce. Graph the sequence and describe its pattern. How high does the ball bounce on its 10th bounce? All right, so on its first bounce, in this case, it's going to go to 4 feet. All right, we don't know how high it started. So our first term, we get 4. So here's our bounce number and our height, if we want to make a table. All right, so how do we get the height of the second bounce then? So where's it going to end up on our graph? And how do we figure that out? So if it only comes to 70% of its previous height, what do I have to do with the 4 and the 70%? What, Sarah? Multiply. All right, so we've got to multiply 4 times 0.7, 70%, since it's only going to 70% of that height. All right, what is 4 times 0.7? 2.8, okay. All right, so bounce 2, it's at 2.8. Okay. All right, what about bounce 3 then? What do I have to do? Okay, 2.8 times 0.7, or, right, we're going to multiply by 0.7 again. All right. When I do that, I get what? Okay, 1.96. All right, so just below 2. Okay. And then we keep going. So if I describe this pattern, what's happening to it? Yeah, I'm just guessing what these are. What's the next one? 1.373. 2. Okay. And then on the fifth bounce, it's what? .96. Okay. Oops. Right. So the graph's going to look like this, right? Is it ever going to go below the x-axis? No, because you're never going to get a negative height on your bounce, right? It's just going to get less and less. So the amount of, so if I describe the pattern, the graph is going to get, it's going to be decreasing at a decreasing rate. Okay, the amount of decrease each time is going to get smaller and smaller. So question is then how high does the ball bounce on its 10th bounce? And so to do that, we could do 4 times 0.7 to the 9th power. Or we could just keep multiplying by 0.7. So we could use our last answer, put in 4, and then times 0.7, and then keep hitting enter. You could do that on your calculator using that last answer feature. Or 4 times 0.7 to the 9th power. And we get 0.16 inches. So on the 10th bounce, her feet be 0.16 feet, approximately. All right, last one. All right, these are called iterations. And using fractals, and all fractals are is that what it means is that there's the next thing that happens is similar to the previous ones. And lots of times with a fractal, we are removing things. Okay. Now this is the example. This is what's in your book for example 5. Okay. So we can see that the Sierpinski triangle is a fractal made by taking an equilateral triangle, removing an equilateral triangle from the center, and repeating for each new triangle. So let's find the number of triangles in the next 2 iterations. So we take one out, we now have 3, right? Okay. If we remove equilateral triangle from each of those 3, we now have 9 of them. Okay? Because this one triangle became 3 triangles. This triangle here became 3. This one here became 3. And that one there became 3. So what are we doing each time? How many triangles are we going to have the next time then? If each one becomes 3, then we're going to be multiplying by 3. Okay? So if I take one triangle out of each of these 9, we are now going to have a lot more. 3 times 9. Okay? All right. Or 27 of them. Okay? All right? And so here's the first one, second one, third one. All right, the fourth one is going to be 27. The fifth one then is going to be 81. All right, so there's actually a pattern here we could use that they're using a formula to find it. A sub n equals 3 to the power of n minus 1, which works for this specific iteration. So then to get the 7th or 8th iterations, which it's impossible to actually draw them by hand, for you to do it, for me to do it. If we had a computer, we could probably do it. But drawing them by hand is difficult. That's why it's important to be able to figure out what is the formula for doing them. In this case, if we did the 7th and 8th iterations, we would end up with quite a few triangles. And this is definitely another one where just using that last answer feature on your calculator works. Because we started with 1, multiply by 3, multiply by 3, multiply by 3, multiply by 3 each time. All right, so how many is in the 7th one, Jordan? 729, okay. And then the 8th one? 1,187, all right. And that's just by continuing to multiply by 3. So here the Cantor set is a fractal form by repeatedly removing the middle third of a line segment, as shown. Find the number of segments in the next 2 iterations. So if I remove the middle third, I'm going from 1 segment to 2 segments. Okay? So which means I'm doing what? I'm not cutting it in half. I'm cutting the line, actually I'm cutting it into 2/3. 2/3 of what it was. But how many lines do I have now? Okay, what are we doing, Danny? Right, how many more lines are we getting then? Every time I cut one, and every time I take a segment out of one, I now have 2, right? Okay, so when I do that, what am I actually doing? But how many lines do I have? Not what happened to that. How many lines do I now have? I have twice as many lines, right? Okay, maybe not. All right, so if I take the middle third out of this one, I have 1 here and 1 here, right? And 1 there and 1 there, 1 there, 1 there, 1 there, and 1 there. Okay, so how many lines do I now have? 8. Okay, so I had 1, 2, 4, 8. What's happening each time? We're multiplying by 2. So the next 2 iterations would give me 8 line segments and 16 line segments. So yes, you're thinking about cutting in half, but no, we're not, because we're actually doubling what we have, the number of lines. Yes, the lines are getting smaller, but what's important is how many lines I have, not the size of them. Okay?